Thank you, Faria. Thank you, Antonino, and all the other partners, of course, of the CO₂ project. I will first introduce myself. I'm Joost Helsen from VITO, the Flemish Institute for Technological Research. And we are involved in the CO₂ project for the development of a 50 kilowatt electrolyzer system and stack. I will, since we are already quite a bit over time, I will keep it short, and this will be a bit of a journey. I will take you on in the upscaling and in the basically the design and development of such an installation. So upscaling, very important part, and resembles a lot for me the development in R&D. So we start with a very small scale lab tests. We try to optimize these in terms of catalyst development, electrode maybe, move towards flow cells, and then try to gradually start stacking these cells and work towards system integration, and finally a demonstration in a pilot, which eventually also could be commercialized. This is kind of the track that also was the subject basically in CO₂, where the final goal would be to develop a 1 megawatt electrolyzer system. So what do these different scales mean? First of all, there's different types of targets in each scale, at each milestone, let's say. So you have, first of all, the lab scale, where you evaluate basically performance and mass balances of your process, try to reach Faraday efficiencies of more than 90% ideally, depends on the process, what is realistic, of course. Typical current densities you want to aim for are around 300 milliamps per square centimeter. And then you also try to find degradation mechanism already, pinpoint the things that could eventually also lead to problems at higher scale. And of course, yeah, reproducibility with multiple cells is already a nice thing to have at that scale. Then we move on to a technical scale, which is a larger single cell, still in the lab, with a stable current density, and also a cell voltage degradation of around 100 microvolts per hour. This is a ballpark figure, things to keep in mind when you're doing this upscaling. I mean, when you're drifting off these targets in a order of magnitude, let's say, then you need to reconsider some stuff. Also, single pass conversion is already important here. So how much of the CO₂ is actually utilized in your process and converted to useful products. And then we move on to a pilot scale. This is also basically the scale at which the presentation deals with, let's say, where 5 to 20 cells of these larger cells, or even a little bit more upscaled, are put together, created a stack, you create a balance of plant, and you run these for at least a few thousand hours, ideally around 5,000 hours, half a year or so to say, with a certain degradation of your cell voltage, of course, and therefore also at that point start to take into account the shunt currents that can occur. I will refer to this later in the presentation. Here you also try to increase, of course, your carbon efficiency, because finally you want to end up with a demo scale or an industrial plant that tries to convert CO₂ as efficiently as possible. A good way and a good point also to evaluate the product specifications in terms of, for example, gas quality or product quality, impurities that are present in the product that you're forming, and also how flexible the system is towards ramping up, ramping down in a setting of renewable energy is, yeah, very important, of course. And then the demo scale is, of course, basically a full stack consisting of at least 50, but mostly 100 or 200 cells, which is a practical limit most of the time, and where you want to operate almost year-round with some down periods. That's why this is a target of 5,000 hours. You will still need frequent maintenance and replacement, maybe of components, before this really becomes a commercial product. But at this stage, let's say the plant will run almost 24/7. So stepping back to the first step, and for CO₂ fuel, we also started in the previous projects like this, and this was also still a bit carried on, as you heard in the past presentation. So you start with a catalyst selection, set some initial boundary conditions on cell voltage and the current density, how efficient your conversion is of current to products in your Faraday efficiency, and then very important, deciding and choosing actually a process which fits best for your purpose. And for example, in our case, the initial discussion was for having a 2-compartment or a 3-compartment setup, as you can see on the right here. Activate the pointer. So a classical GDE system with the membrane in the middle and 2 liquid electrolyte compartments, but with a gas supply from the backside. A very efficient system, however, difficult to scale up and also difficult to stack, compared to the one that we chose for CO₂ fuel, which is basically a zero gap system where the bipolar plates are directly contacting with the electrode, and we have still a liquid analyte. So, turning back to the core of the presentation, namely the development of a balance of plant, so an electrolyzer system. What does that mean? How should we go about? First, we develop or we build a process flow diagram, and that's based initially at the first point based on a simple mass flow diagram. As you can see here, this was the mass flow diagram which was drafted for CO₂ fuel. You simply calculate the number of cells that you need given a certain geometry, and assumptions on Faraday efficiency, CO₂ utilization, cell potential, and current density will give you an output in terms of oxygen generation and also product generation. So in our case, this was mainly focused on hydrogen, carbon monoxide, and ethylene. From this process flow diagram, or from this basic mass flow scheme, we will then convert it later on to a full P&ID idea. But first I want to mention a few things about the stack itself. So the cell, unfortunately, I cannot disclose the internals and the designs of the stack which we designed for CO₂ fuel, since we are still in the process of patenting it. But I can share you some general thoughts, and I think it's very useful as well. And these considerations have all crossed also our work for CO₂ fuel for the larger stack. Some considerations that are very typical when designing a stack. And first of all, this is about cell flow characteristics, because this is the first thing that changes when you start upscaling from a small cell in the lab to a larger cell. You need to be aware of how liquids and gases, but also two-phase flow. So liquid, including gases. Remember we're making oxygen, we're making hydrogen. So there is always gas involved, and many times it's a two-phase flow. How do these behave in the cell that you're designing? Also, you have to take into account the specifications of the membrane electrode assembly, the thickness, the hydrophobicity, the conductivity of the MEA. And then, of course, will you go for a monopolar, for a bipolar design? In many cases, of course, for industrial applications, we will choose to go for a bipolar design for obvious reasons, but it's still a consideration. Then the aspect ratio, the ratio height to width, that's also a very important one. And then, of course, we are designing, in this case at least, a pressurized stack. So also regulations come into place, and in this case it's the PED directive, European directive on pressure vessels, which we need to abide with. So that's a very important one. In terms of design, so you see here basically this is a 400 square centimeter cell design. These are 10 cells assembled together, consisting of different bipolar plates, MEAs, electrodes, and of course anode and cathode compartments. But important to take into account when designing a cell, and this was also one of the things that we are still trying to solve actually for CO₂ fuel, is the occurrence of shunt currents, and this typically occurs in alkaline electrolysis, but also in alkaline CO₂ electrolysis, where KOH is used as an anolyte, which is basically a conductive liquid, which is contacting all the different bipolar plates at a different potential, and hence also can produce hydrogen in the anodic loop, contributing again to hydrogen in your oxygen compartment, and this is of course a very much undesired phenomenon. Next to that, also pressure drops are very important. You need to make sure that you have, on the one hand, not too much pressure drop across the channel, so let's say from top to bottom, so that liquid can flow freely inside your compartment. But on the other end, you also want to create sufficient pressure drop so that the liquid which is pushed from one side also reaches the last cell. So that's very much an important thing to take into account when designing these cells. And of course, mechanical and chemical stability of all the components that you're using is crucial, because once this is not sufficient and the stack will fail, then of course your system will shut down. Also, simulation results can help, and especially for the mechanical stability, we have done on that same stack, and also for the CO₂ fuel stack, simulations to really try to pinpoint a certain stress points where von Mises stresses can accumulate and create potential problems in relation to the used materials. So if we exceed the limits, the tensile strength limits, for example, of certain polymers, this is a tool that we can use to identify this prior to actually constructing the cell. Very important when using pressurized systems, pressurized stacks. Why do we want to pressurize, by the way? That's the main goal here is to have higher concentration of CO₂ at the reaction site. So increased system pressure will lead to increased partial pressure of CO₂, hence also an increased reactivity. So the sealing is extremely important in these stacks, and there's mainly two types of sealing that you can use. There is O-ring sealing, of course, and flat gaskets. Flat gaskets have some, both actually have advantages and disadvantages. For the CO₂ fuel project, we used the O-ring type. And then, of course, the material, as well as for the structural plates for the rest of the stack, is important. Also, in this case, sealing material is quite important, especially related to resistance to organics, but also degradation to high oxygen concentrations, for example. Finally, when a stack is built, it can be pressure tested, and together with material certificates, risk analysis, and design calculation, and finally also a manual, we aim, and we actually did achieve the EC conformity, and this is also necessary when you want to deploy this kind of equipment, so the stack in an industrial environment. This is actually a picture of the CO₂ fuel stack, a close-up picture of the two flanges with, in this case, as you can see, this very thin bipolar plates inside. These are 25 cells stacked together. So it's still, let's say, a short stack, but this can be upscaled quite easily to 100 cells. And this was pressure tested at 45 bar, which means that you can operate this stack at around 30 bars. Then the next step, so we have a stack designed, constructed. The next step would be to design also a balance of plant. So an electrolyzer system providing all the liquid flows, the instrumentation, power supply, etc., etc. The starting point here is always the process flow diagram. And from this process flow diagram, we will then draw a detailed process and instrumentation diagram, which can be finalized after some iterations, and then an initial hazard analysis is carried out. Components are actually drafted from this PNID and are selected. We can make a 3D process layout. Purchase processing has to start. There's a very elaborate process actually of sourcing out all the components. Of course, all these things, all these instruments have to be assembled in some kind of mobile platform. At least that was the objective in CO₂ fuel. So we chose a container also, and this needs to be laid out very carefully in order to make sure that all the connections are met in a logical way, and there is no conflicts there. And then finally, also after the construction, you need to do a final hazard analysis, and this is based on the as-built PNID, as we say, because during the building still some small changes can happen, and how these affect the hazard analysis should be evaluated before finally reaching the EC conformity and the certification tests. And then finally, you can run some factory acceptance test, which is functional testing, and site acceptance tests at, for example, an industrial site where you connect it to the existing utilities of the plant. This is how the PNID of the CO₂ fuel system looked like. I've marked up the two main loops here. So we have the red loop starting from tank 1, which is the cathodic loop and runs over the stack, which is here in the center. And then the green one is the anodic loop, our KOH liquid cycle, basically. As you may have understood, the cathodic loop is a gas loop. So we provide CO₂ directly to the stack, and all the products that are formed in the stack, either gaseous or, for example, we also see some ethanol and propanol being formed. These are kept in a gaseous state. We operate the stack at 60 degrees approximately, but are then condensed out in this condenser. So all the condensable products are also collected in this tank. We have the option for this balance of plant to recycle the CO₂ gas. So then we can operate at certain levels of conversion, which can be interesting to study indeed how many cycles you have to run in order to get a certain conversion. This is the second part of the PNID, more focused on the CO₂ supply, and also the green lines here are what we call the inerting lines. Before we start up the whole process, we have to make sure that everything is safe, in order no residual hydrogen is left in the installation, for example. So we flush the whole system with CO₂. This is also measured continuously at the outlet in order to ensure a safe operation. This part is on the water supply, so water supply for filling up the tanks, for example, and also for making up the KOH, 1 molar KOH solution. If we convert then this PNID into actual 3D layout, then this is how it looks like. So we make a full 3D layout. All these components that you see schematically in the previous picture of the PNID are here drawn in 3D in order to make sure that these fit into the container. Then the next part, so the container layout itself. I can be quick about this, but basically this is a scheme of a 20-foot high cube container, separated in 3 parts. We have the main part, the ATEX zone, which is the explosion-proof zone, also guarded by different sensors and LEL cells, sensors, fire detectors, etc., in order to make sure that any leakages that might happen here are not going to be leading to any kind of explosive situation. Then we have a dry compartment, separate compartment here, where the full control system is located, and power supply, and also the electrical cabinet. And then there is a wet, so to say, wet compartment, including the liquid storages and the makeup of new KOH solutions. This is the screen of how the automation panel looks like. So everything is fully automated through a PLC and safety PLC, fully industrially compliant. And then this is one of the pictures of the balance of plant. So we finished the mechanical assembly. Then after this mechanical assembly, a lot of wiring needs to be done to trace all the instruments, valves, pumps, conductivity sensors, pressure transmitters, etc., to trace all these wires through the electrical cabinet, where the automation is actually linked in to these wires. After automation has finished, then there is a very important step, which is the I/O testing, making sure that all that PLC communicates with each of these instruments. Of course, a pressure testing afterwards, making sure that we do not have any leaks, because there's, as you can see, it's a very intricate design with a lot of couplings where leakages can occur. And then after the pressure testing, we have a functional testing and a final factory acceptance test. These are some pictures of the balance of plant. This is obviously from the ATEX zone, so where the two tanks are located, as you can see here. So the behind this is the anodic tank, and in front you will see here the cathodic tank. These are, for example, some sensors for the ATEX environment. Another view of the on the left of the anodic tank. This is still a view when before the factory acceptance test, because now actually this is fully insulated and traced as well, so we can keep the KOH loop at 60 degrees. Here you will see the part that I didn't talk about yet, is the construction or the structure that will hold the stack itself. And so you have the power supply lines coming from the control room where the automation panel is, supplying these six.
Joost,
yes.
very sorry to interrupt. I think we have to speed up because we're
I'm
already
finishing.
over time.
I'm finishing almost. It's just a few pictures,
perfect.
so that's 2 more minutes.
Okay. All right. Thank you.
So we have the power lines supplying to the place where actually the stack will be situated, and this is it. So this is the stack, as you can see on the same structure, and this is how it's fit into the balance of plant. So to sum up, we have a very unique, build a very unique mobile infrastructure in Eco2Fuel, 50 kilowatt plant with which can run stacks at up to more than 100 volts and almost 1,000 amps of current at pressures up to 16 bars and 60 degrees Celsius, which is a gas liquid process, fully ATEX and PD certified and automated by PLC. The stack itself, as you can see here, is a 1,500 square centimeter stack. This one is rated to 30 bars and is based on a rectangular design with very thin, as I showed in the previous pictures, a very thin compartments. One thing to still keep in mind is that, we're still optimizing this stack, so it's still under development, let's say, and the main point here is to reduce further the shunt currents that are occurring. This is how we would like to see it running at an industrial site, but that's hopefully for the coming months or coming year. So thank you very much for your attention. And if you have any questions, I hope, Faria, that you can moderate a bit, because I had a bit of an issue with understanding the questions from the room itself in the previous speaker. So if there's any questions from the room, please rephrase them for me. Thank you.
Yes, sure. I'll try. Yeah, thank you, Joost. Yes, thank you for sharing all the details and complexity that goes on with the design of the electrolyzer and the balance of plant itself. So we'd like to ask if audience has any questions. Okay, no questions from the audience, but there are questions on the chat. Excellent talk. Is there a limit to how many cells you can stack? And with regards to the CO2 flow and current, are cells in series or parallel?
So this is a typical bipolar design. So we have all the cells in parallel. The number of cells that we could stack, we didn't, let's say, reach an upper limit yet, but this stack is designed for at least 100 cells. So that's kind of a practical limit, especially when you consider the complexity of the assembly itself.
Okay. And next one, the stack has to be flushed with DI every 50 hours. Is that also automated? Question mark. Also,
Yes.
how do you maintain the pH of the analyte to ensure that it is still alkaline, or would it eventually become carbonated?
True. So pH of the analyte will gradually decrease, but we have an automated system and also a conductivity measurement, of course, in the analyte loop. Whenever the conductivity goes, for example, below pH 11 or 12, concentrated KOH is added to the loop. And the first part of the question was, I don't remember.
Is the flushing automated?
Yes, of course. Yes. Yeah, I didn't specifically indicate this in the PNID, but there is a flushing line as well, and we have also tested it. So we're able to flush the stack when it's still under pressure. Of course, we will cut the voltage at that point. So the electrical voltage will be shut, and the flushing will then, from tank 1, will flush over the cathode and will then evacuate basically any kind of salt precipitation or remaining products that are in the cathode.
Yeah, there are a lot of questions, but I'll take one last one. Thank you for the excellent presentation. Why is the stack kept tilted, not vertical or horizontal? Many thanks.
This is basically for having a gravitational evacuation of products, liquid products that would be formed in the cathode. So by this inclination, we ensure that the cathode, the stack can fully drain. So once it's also once it's disconnected, it can fully drain in the position that it's in this case. Also for the anodic loop, it's important to make sure that gas can be evacuated and there's no accumulation of gas inside the different compartments, anodic compartments, so that you don't have any gas pockets.
All right, there are many more questions, but because we have time limitations, this will be the end of question answer. Thank you once again, Joost.
You can always people can always contact me, of course. I put my email there, so feel free to ask any questions via mail.
Yes. Also, his information will be on the Equitable website available. Also, it's also there. Thanks. Thank you so much, Joost, once again.
You're welcome. Thank you.
I hope you can hear the class from the audience too.
No, it's not, but I believe you.
All right. So this is the end. Thank you. Thank you, everybody who attended online and in person for the workshop.